Recording is on.
Okay, awesome. Thank you, everyone. So today I'm going to explain some basic algorithm on linked list, like implementing a stack using linked list, and then we will see if we have some time. This is the new program which I want to cover. This is like creating copy of immutable list. So, but let's get back to the first one. The basic idea is creating a linked list, creating a stack, right? So let's open new whiteboard here. So yeah, so we all know linked list here, right? Linked list has kind of nodes and address. So here is a node data here, and this will be the address, right? So now what we need to do, so we all know that uh, the main thing, adding an element is easy if you want to add at the front, right? So if you want to navigate, you need to navigate the address of each element, right? So um, and what the so the let's say what is the traversing. If you want to traverse n elements, so order of n is the traversing. So you need to traverse. Let's say you want the element at third element. If you want the third element, you need to traverse from the first, like 1 2 3. That's the only way. It's not like a of 3 or a of 2. Like in case of arrays, third element is a of 2, right? Simple, just order of 1. You can simply directly access the, this is let's assume this is array, or you can also think of an array like this, right? So 0 1 2 3, and if you want third element, simply say a of 2. You will get the element directly with just order of 1 time complexity. There is, you can directly get the value third element. But in case of linked list, you need to navigate from the head. So there is a head pointer, and you need to navigate from the beginning. So that's the difference between linked list and arrays. So now, let's implement a stack using linked list. So it's yeah. So everybody know that stack. We can think of stack as like this, right? So first in, first out, first in, first out. That's the stack, right? So whatever you putting on the stack, that will be the one it comes out, right? So I want to pause here, and let's see how can we implement this stack behavior using linked list, right? So yeah, let's start a kind of collaboration session. I like these sessions are, I want to make it like collaborative and talkative. So anybody want to share how can we do this, and um, how to do this, how to implement a stack in the linked list? I think we covered this before.
Yeah,
I would like to hear from anyone. Yeah.
yeah. Usually in a linked list, we'll hold the address of the first node in a head pointer. So
Mhm.
as it is, we are going to hold the first node of the stack in top, the address of the first node in top, which is the top pointer. So
Yeah.
if you want to push a new element into the linked list, which is in the form of stack, we are about to insert it in the front and change the address of the top,
Yes.
and deleting it is from the front, and also it changes the address of the top.
Exactly. Yeah.
Yeah.
Awesome. So basically, the main operation here is in the stack is like a push, right? Push is one operation where push means like, yeah, hey, I want to push number 4, number 5. You will give the data. So once you get the data, what you do is we're going to create a node. So as I said, first in, first out, or that's how we call FIFO, right? Like the stack, right? What first in? Oh no, no, it's not. It's not first in, first out. Sorry, it's last in, first out, right? Last in, first out. LIFO. Correct me if I'm wrong, right? So whatever the last in element, this is the last element, that will be the first out, right? I think first in, first out is Q. Correct me if I'm wrong. So now, so last in, first out. So last in, whatever the last element you are putting, that should be the first one to come out, right? So how can we do that? As Karnya mentioned, by just adding that element at the beginning. So usually if I say add, we are going to add at the end. That's a pretty common thing what we do, right? If you are in arrays or anything, add an element, it will go to the, you add at the end. But instead of adding at the end, because if you are adding at the end every time, if you say pop, you need to navigate all the way to the end and then you need to pop this element. It is tough, right? So rather than that, you simply add the element at the beginning, right? If you are adding, if you say push, and then we'll create a node and we will add before the first element, right? And then we will change the address of that. That way we can get the if we say pop, we can get that element really quickly. We know head points to the top element, and we can simply pop that element, and we then change the address of the head to the next element in the linked list. So push and pop are the main operations, and what are the other other operations usually on the stack?
Peak.
There are two more. Yeah, peak is another one. So there is one more. I think most of the languages will support size or length, right? Size. Basically, at any point of time, hey, give me what is the length of the stack or size of the stack. Okay. So how can we do this? So peak is basically, peak means it will just give you the value of the first element. It won't remove the element, right? So hey, tell me what is the value here. So I don't want to pop the element, but I want to know what is the value of that element, right? So that's very easy, right? Because the head is pointed to the first element. We just simply say head data, whatever the data. You'll say, hey, here is the element you want. Here is the data you want. You can simply return that. That's a peak. And size, how can we maintain the size? Like if I say, hey, tell me the size of the size of the stack. So are you going to are you going to count? Are you going to traverse the stack and tell me the count? Let's say if we have 50 or 1,000, like every time if I say size, are you going to count the elements? What is the best way to you know do that? Yeah, anyone want to share anything on that? How can we do that in an effective way? Is that Vanilla? You want to say something? Go ahead.
Um, means are you asking the count of the array list or the stack one?
Stack here. Basically we are implementing a stack using linked list, right?
Yes.
The main problem here is we don't want to use the existing stack data structure which is available in C# or Java. Every language provides stack. The problem here is you want to implement that stack. How the stack can be implemented using the data structure linked list. Okay. So now we just discussed the push, pop, and peak, and how can we get the size? If I say, hey, what is the stack dot size? So the only way in the linked list is you need to count, right? You need to navigate from the first element, and you need to count all the elements and tell me, okay, this one has 4 elements, so size equal to 4.
Yes.
What is the other best mechanism to, because the problem here is every time if you say size, you need to navigate to all the elements, and you need to give the size. What is the other best mechanism? Very simple question here, right? I want to tell you the size immediately. Like this, it's not order of n. I don't want to count every time. So how can we make it a little better?
So when we are popping itself, we can have a single go when we are popping itself, or
Hmm.
when we are pushing itself, we can have a counter in the mechanism.
Exactly. That's exactly the answer I'm looking for. Just maintaining a counter. Basically, a counter. We will increment as you are pushing the elements. If you are pushing the elements, we will increment the counter. If we are popping the element, we will decrement the counter. At any point of time, we want to make sure that counter represents the number of elements on the linked list. Okay. So whenever we initialized with 0, because when we initialize the whole stack, that there is no elements, so initially it will be 0, and as you are pushing, will increment. If you are popping, will decrement. So that's the main thing here. So yeah, last in first out. This is implementation. Let's go through the code. Unless if anyone have any other questions, I can I can pause here. So yeah, hello Shubhagar, any questions, or is it clear, or I just want to make sure
Uh,
following and
it is clear, and but I can't see
yeah.
your screen, and for some reason I only see my. Are you sharing
Oh
anything only now?
yeah, I'm sharing the whiteboard here. Sorry, and is it the same thing for others?
No,
I can see
no.
Can
the
you?
screen.
You need to accept the. So in the first time when you are opening this Git site, meeting.gist, it will ask to have a permissions to allow the microphones and all the screen shares
I
and
said hello. I did say hello. Maybe
No, no,
I
I
did.
think that should be the sharing. If I'm sharing, I need to allow, right? So I already allowed. So all of you guys can see, right? Cecilia, Karanya, and Vanilla. I just want to confirm. See
yes.
the
We can
Ah,
see.
right.
I can see it. Sorry, I think I was looking at it wrong. I can see it now. I think. Okay, sorry. I have two sessions open. Maybe. Okay, sir. I can see it now. Sorry.
No
I can
problem,
see
no
it now.
problem. So I
Yeah,
just want to make
I can see it now.
great,
Yes.
great. You can see the whiteboard here, right? So basically, as I said, I explained this is a stack, how the stack looks like, right? So I want to repeat again. So here is a stack look like, and we want to implement, we want to push the elements, and we want to pop the elements, right? So here is the stack, push, pop, peek, and size methods we want to implement. So we want to implement this behavior using the linker list. Here is the linker list, right? So is that he joined? He's going to, maybe he's going to rejoin. Yeah, let's wait for a minute. In the meantime, what I do is, okay. Hello, Andy. Yeah, Shivagaru. Yeah.
I can see it now, Andy. Okay. Thank you, Andy.
No problem. You can see the whiteboard here, right? So
Yes.
yeah, we want to implement this stack. We want to implement this stack behavior using a linker list, using a data structure linker list. So, so linker list has two main properties or the things, right? One is data, whatever the data you can put it there, and the second one is the address of the next element, right? This is the basic construct of a linker list. So whenever we are adding a new element, if we are adding a new element here, we basically need to create a node, and then we need to manipulate the address. So how can we manipulate the address? Basically, we are pushing the elements. Whenever we say like 1 2, so 1 will be here, 2 will be here, 2 on the top. If I say 3, we want to create an element called 3 here, and 3 should link to 2. And the top, there is a top or head. You can, linked list has another property called head. Head is the main pointer that points to the first element of the linked list. So head points to 3, and 3 points to 2, 2 points to 1. So now it's a kind of 3 2 1, but I inserted 1 2 3. Now if I insert 5 here, after 3 5, 5 should be on the top of the linked list. So what I do is, I will create a new node called 5, and 5 should link to, what is the top element? 3, right? It should link to 3, and then head points to 5. So now if I anytime if I call pop or peak, that's the top element is 5. So I can pop the element 5, or if you want me to peak is basically display the value or give me the value. I can give you the value 5, because that's the top element, right? I hope it is clear.
Yes.
So yeah, so now I'm going to show the code. Actually, what I'm doing here is I'm doing two things. One is sharing the code through online GDB website here. Yeah, and also I'm running locally in a Visual Studio Code actually. So okay, now let's do this. So um, here is the class I created. Basically, node is a node, represents the node data structure. As I said, node has two things, right? Data, and then next variable. What is the next pointer? No, next is itself is another node, right? So this is how they construct. So every node has a data property, and another node which is a pointer to the next element. So that's a kind of a data type is node, because that's connected to the next element in the linker list. So this is a basic node class, and this is what the algorithm is for. So it is the you guys can see my screen here, right? The online GDB, right?
Yes. Yes.
So here is the node class. This represents the one node in the linker list, and the second one is a stack. This is the main algorithm we are going to build. We are going to create a class called stack that have all these methods. As I said, push, pop, and top. That's it. So top or peak, this is exactly the same as a peak. And then size is a public property we are going to maintain. So we are creating a stack class. Basically we are creating a library kind of thing. You are creating a stack, and that can be used by anybody in your program. So this is the main program. This program will use the stack what I created on the above screen. So this is a driver of the program, right? So now let's go ahead and look at the each of the methods. So we just discussed. So we are going to see how we implement it. Okay. So the first one, node head. So as I said, we need to maintain the head pointer. This is a head which we initialize with null. Initially, when you create a stack, there is no elements. It's a null, and head points to null, and the size is 0. This is a constructor, right? So we are initializing with 0. Right now there is no elements, and it's a public property. The size can be accessed by anybody who is creating an instance of the class. So I hope everybody know about this object oriented paradigm, and so I'm not touching more on that. So it's a public property, and anybody can access size using the object. So now push, here is a push. As I said, push method, and here is the value. I want to push a value 5 or value 6 or value 1 into the stack. I don't care how you maintain. Like basically the main algorithm is always talks about the data, right? I don't care whether you create a node or whether you create something. We are just using stack from C# or Java library. It will use its own data structure. That's what we are using. We are using our own node class, which is not exposed to the, basically it could be the inner class inside this. We are not going to expose this most of the times to the driver class. Okay. But here let's see. Now I'm saying like push v. I want to push the element v, whatever the value here. So as I said before, we are going to create a node here, new node. So with value v. So node, if I go back to the node here, I created a constructor called constructor with which taking value, and I'm putting the value in the data variable and putting a null value for the next element. Whenever you're creating a new node, right? Basically, as I said here, we created a node 5. Initially, when you create this node 1, we'll create with value 5 and with an empty, empty or null value reference. That's the initial thing. So now what are we doing? We created a node, and then we are checking whether head is null or not. If head is null, that means there is no elements. It's just one element, like the first element you are creating. That's why simply say head equal to n. Whatever the element you created, that is the head of the linked list or head of the first element in the stack. Else, what we are going to do? N dot next equal to head. Basically, n means the new element what you created, and the next address we are saying the next address of the new node is a head. That means we are connecting here. If you look at here, we are connecting 5 to the head. Currently head pointed to the 3, right? We are connecting what is the next value, next address of the 5 is head, whatever the head value here. So if we really want to go in deep into the address level, so we can simply say 3 is stored in the address 1112. Let's say that's the address of the node inside the memory. That's what head reference, right? Head value is 1112. That means it will go to the node 3. Now what are we doing is 5 dot next equal to 1112. That means whenever you say 5 dot next, it will connect to the node 3, because that is the address of the node. Now both head and the end dot next pointed to the same element at this point. Now what are we doing? The next step is basically, sorry, next step is here, right? Basically we are saying head equal to n. Simple. We are changing the head value because we already stored the value of head, the address of the first element in the new element. Now we are safe. We can safely override the head. Now head equal to n. That means whatever the address of the n. So if I go back to the diagram, let's say the new node 5 was 1165. That's the address of the new node. That will be the head value. So now head points it to 1165 inside the memory. That is the first node of the linker list. Is that clear?
Yeah.
Yeah. Thank you. So now we completely completed the push operation here. We create a new node and we checked if the head is there. That will be, if the head is null, that the new node will be the head. Otherwise, we are putting the next node, next address. We are updating the next address of the new node to point to the head, and then we updated the head to become the new node. So now we are successfully completed inserting the element at the beginning of the linker list. That's what the push means. The way we implementing is we are adding the element at the front of the linker list. And at the same time, as I said, we want to increment the size because we size was 0, now size is 1. So as we are pushing more elements, the size keeps increasing. So we no need to navigate every time. If I say, hey, give me the size, otherwise we need to write a for loop. We need to write a for loop, and we need to navigate all the elements and then count the elements every time. We don't want to do that. That's a kind of lengthy process or time taking, and that's order of n complexity. So instead, we simply maintaining a counter, very easy to find out how many elements. So array provides the size, right? Array has the length or size, whatever the length, it will automatically give you like a dot length, or it will give you in simply, because whenever you are declaring or when you are creating array, we will upfront, we will say, hey, this array size is 100 or 200. You are going to you're going to mention how many elements you want to store, and it will also has its own size. The length will give you how many elements in the array. But in the stack or in the linker list, that's not the case, right? Linker list don't give you anything. Linker list is complete manipulation of addresses inside the memory. It's completely on us, like on the developer who is using the linker list, need to implement everything. So now size incremented. Now the next one is pop. Okay, so how can we do the element, like if you want to pop the element, right? If I say pop, so I'm expecting an integer. Always I expect an integer because I'm putting the integers, I'm pushing the integers, I'm expecting integer value. Okay, now here is the thing, this is the condition, very important. This is one of the interviews, in interviews where they will observe you're writing these kind of boundary conditions, or the what we call the exception cases, not boundary conditions. These are all kind of base, or the exception cases. Basically, if the head is null, right, we should not even proceed anything. Head is null means stack is empty. Basically, there is no elements. There are no elements in the linked list, but you are asking me to give me an element, pop. So that's where we need to throw an exception. So head is null. Head is null means, like, head is on the top here, which is null. That means you just created an object, but you did not push anything, but you are trying to pop an element. That's where we will say stack is empty, right? So then when we all know that when you say throw new exception, it will not execute any of the rest of the lines in the code. It will just return the value, return the exception to the calling program. So That's why we no need to write any return or anything. Now we will simply come here. If the control comes here, there is a head value. There is an element, at least one element. That's why we are simply saying head dot data is the value v, and we already copied the data. We simply say head equal to head dot next. We are proceeding. We are updating the head, the address on the head to the next address of the next address in the linker list. So basically next node. So it could be the null. Let's say if we have only one node, let's assume that only one node, our stack has only one element. That means head pointed to this element, but the next value is null. So immediately when you remove this element, head becomes null, because head equal to head dot next, which is null. So that's okay. That means stack became empty that point of time. That's the reason we are decrementing the size. Since you updated the head address, that means you progress an element in the linked list. We are simply decreasing the size. So you might ask, hey, where did we do the deletion of the node? We did not delete the node, right? So the intention here is the updating the addresses, not the real management of the memory. So I don't care whether whether you remove the element or not, because that's not the intention of the algorithms here, right? That means what I'm saying is we deleted the, let's say you say pop element, we deleted the first element here, right? Let me change some color. Okay, so you deleted the element here, but we are not deleting the memory. Basically, that will be taken care by garbage collector. So it's not like C++ or other low level language we are writing. So let's assume if you are using C# or Java, so no need to worry about the deletion of the node at this point of time. So simply we are updating the address, and we are proceeding to the next line. So side minus minus, and then size became like reduced, and we are going to return the value. So here is the value which we just put aside before proceeding the head, right, to the next element. So that's the pop. So let me know anytime. Stop me. Feel free to stop me anytime if you have any questions. If anyone have any questions, okay. And the last one is, as I said, top or peak. This is a peak. I don't know why I cannot write it here. Oh, maybe I did not log in this browser. I don't know. So, but anyway, pop or peak. This is basically, hey, give me the data of the top element, right? That just head dot data. That's it. So if the head is null, same case, stack is empty. You're asking me to give the top element, but there are no elements. Head is null means there are no elements. So otherwise it will give you the data. So here we did not update any size, we did not do any address manipulations, because this top is just, you want to give the data of the top element. So that's the implementation of the basic stack algorithm. So now if I go ahead and show you the main driver here, so this is simply I'm creating a stack here, and I'm pushing three values, 1 2 3, and the top element is s dot top element should be 3, right? So let's see, we can run the problem and see the answers along the way. So yeah, so see, I pushed three elements, and the s dot top will give you the top element number 3, and s dot size will give you the size 3, and then I'm popping the element like s dot pop. So it will pop the element number 3. Basically, that's the element which is on the top. And then if I say top element, it will give you 2. And if I say, now I'm saying like push 4 and push 5, right? And the top element should be 5. That's what I'm expecting, and I got the 5. And the size is 4. Size is 4 because I removed 3 here, right? 1 2 3 4 5. But before inserting 4, I removed 3. That's why the size is still maintained as 4. So any questions so far, or do you want me to explain any of these again? Anyone like Karanya,
No,
Cicely, or Vinny? Yeah. Is it
no.
clear, or yeah? So is it helpful just to kind of give a kind of baseline kind of? This is how I explain, like, what is the problem we are tackling, and how it works, and how to approach the algorithm, and then I'm going to show the code. Okay. Um, Usually we can discuss the complexities. Let's see it's very simple to tell for this, I think. So let's see, anyone can answer what is the complexity of push operation, time complexity or space complexity.
Of one.
Order
Of
of one. Yeah. Yeah. Okay. And pop is also same thing, right?
yeah.
Of one, because we are not navigating the whole data structure. We don't care how many elements. Basically, either the push and pop, we are just operating at the beginning of the linked list. We don't care how many elements, even though like 10 elements or 50 elements or 1,000 elements. We are just updating the you know front of the linked list. So it's order of one, always the same thing. Even the size increases, even the number of times, it's the same thing. So um, um, yeah, basically, if you are inserting at the end, let's say you are always like inserting, like if I say 1 2 3, you want to insert like this 1 2 3. And if I insert say 4, if you want to insert at the end of the linker list, what would be the order of push and pop? Anyone can tell? I want to insert the new elements only at the end, let's say 4 and 5.
Order of n.
Exactly, order of n. So every time, because if I want to insert the same way, if I say push 5 again, I need to navigate all the elements, and then I need to add new element at the end. And same time, if I want to remove, I need to navigate all the elements at least, and then remove the last element. It's a tedious process, and it's not worth doing it that way, because it's always time consuming process. This is all matters, right? When we are writing an algorithm, when you are writing a program, and if you look at a lot of products, every product is what we are using, Slack or this even Google Meet or even this just a meeting, every little things are really matters, right? All this very small manipulation of memory is really matters. So because when we are developing these kind of products, it's always run on the others machines, right? Like right now we are talking on this just a meeting. So now this is running on a browser, and I'm sharing the screen, I'm talking, and have videos and audios, everything need to coordinate, and the transition has to happen really quick. So all these have memory management in some behind the scenes. It has to allocate the memory, and it has to process the audio signal, video signal, and then and this whiteboarding signal, and all this screen sharing, everything converted into the bits and ones and zeros and bits, and transmission has to happen, right? So all this memory management is a very complex topic when we are go deep to those levels and writing products, and then this really matters. That's why this is another reason why the companies will touch on these. Basically, if you want to in those kind of development teams, you definitely need to know the memory management, how to do this. So most of these in-depth components are in C++, and those kind of things where it really matters. So they may not be in the abstract languages like C Sharp or Java. There could be some components on top, but real things will happen, in the C++ world, which always, concerned about the memory management. So, yeah, I hope it helps. So if no other questions, we can jump to the next algorithm. But if it is like kind of late or something, then we can just discuss the algorithm, and we can. I will just explain the what is the problem, and then we can go to the next week and look at the code and everything. So, any questions on the existing one? Okay, I will
No,
take the next.
Suresh, but I have a personal question. What is meant by expensive operations? Yeah.
Expensive operations means the processing. Basically, if you look, consider the same exact same algorithm, if you are adding the element at the end, right? Let's say you have just think about a million elements or a 500, like 200k or 300k elements, like 3 lakhs or 4 lakhs elements in a single linked list. You want to add at the end. If you want to add at the end, you need to process all the elements, right? So expensive in the sense, in terms of time, basically. It's not like money, right? So it is money as well. So if you are running, like, all of our algorithms, all of these programs and codes is running on servers, cloud servers, right? So if they are taking long time to process, they will consume a lot of memory, they will consume a lot of power, they definitely take a lot of time. So the users will frustrate if I don't get the immediate answer, right? Let's right now, if you are doing all these online transactions, every time they will say OTP. How quickly you will get the OTP code, right? If you need to wait for 10 minutes for OTP, who will wait for that? You need to do something else, right? So that is the quick thing. Processing means expensive in terms of time, expensive in terms of processing power, and expensive in terms of complexity. So even if someone want to understand your code, they cannot understand if you are writing 100 lines and a lot of while loops. This say exact same algorithm you can do by adding at the end, but adding at the end requires the for loops. You are adding more lines. Basically, it's expensive in all different angles, right? So maintaining the code and running the code and the power usage and memory usage, and ultimately consumer satisfaction. They don't satisfy with the code what we are writing, because it's performing poorly, right? Did
Okay.
I answer? That's what it is basically.
Thank you.
Yeah. So in this algorithm, we wrote the code without even navigating the elements in the linked list. We are just updating the address or the head. We are just inserting at the beginning, and we are done. So, but let's consider, if you want to implement a queue. Everybody know about the queue, right? Let's try about implementing a queue using a linked list. How can we do that? So queue is something like this: insertion happens at one end and removal happens the other end. That is the first in first out. That's actually the FIFO, right? First in first out. So whoever comes into the queue, they will come out. It's like railway reservation queue or anything, right? So how can we implement that kind of queue in a linked list? Just think broadly. How can we do that? So let's assume that here is this board is already like kind of vast. We can take one thing. We can take new one. It's a good to discuss. Yeah, I think it's good for this discussion. So let's say you want to insert. This is the first in, and this is the last out. Like first in. Sorry, before first in, first out, right? Yeah, first in, first out. So now, how can we do in a linked list? Just think. I'm also don't know the algorithm. I'm just thinking along with you guys. So let's say first in, yeah, before first in, first out. Let's say if I add 1, 2, 3, 4, if I say Q, right? If we Q has NQ and DQ, right? NQ and DQ. NQ means basically it will add an element, and then DQ basically remove an element, right? So if I say NQ1, it will be here, and 2, it will be here, and 3 and 4. Now if I say DQ, I want to remove this element. I don't want to remove the 4, right? Whatever the element which is inserted at the first, that should be the one we need to remove. Correct? So now if I say DQ1, so DQ, if I say just DQ, you need to DQ this last element. And if I say NQ, I need to insert at the beginning, right? I think this is there is a one data structure which really best suited for this. Can anyone tell? So if it is a linked list, this is a single linked list. Single linked list always have pointed to the head element. But if you want to DQ, you you need the last element, right? Let's say you are inserting this way. The queue is like this. Railway reservation queue is like this. One guy entered. We are putting one guy on the top of the line. Another guy entered like two. Okay, stand here. Three stand here. Four stand here. Five stand here. Now this guy got the tickets. That means we need to remove this element. And this second one, here is the number two. He will be the front in the line, right? So how can we remove this? We need to navigate all the way from here. If you are only having a reference head element only point to the first element here, you cannot remove one unless you navigate all the elements. So what is the best way?
You should also have reference to both first and last elements. That's how you can do it better.
Exactly. That's exactly that. Thank you for that. So here is the head and here is the rear. Rear, or the you can think of as a this is the starting of the queue basically. This is the head of the linked list and rear of the linked list. But the problem here is, even though you have reference here, can you remove on itself? There is a problem with the linked list. Single linked list, this rear points to number one. You cannot remove one on its own, because if you want to remove number one, basically you need to update the address of number two. That is what the removal of number one means. This is something we discussed a week ago or before. So the main intention of removing an element is basically updating the next address of the previous element. That is what the removal. Basically, if you say next of 2 equal to null, that represents you are removing number one. Correct? Then now here you have rear, which is pointed to this last element. How can you make the next address of the number two to null? Because from rear you cannot go back, because the only next pointer, there is no previous pointer here. You cannot go back and update this next value. I think I already gave you the clue. How can we do this
We
in a
can
better way?
so whether we can
Yeah,
do
go ahead.
a doubly linked list, or we need to
Exactly.
go to integrate iterate each and element to n minus one, and we can do
Exactly.
another.
Awesome. That's exact answer I'm looking for. There are only two solutions. One is, again, as I said, every time you need to navigate from the beginning and remove the element. The NQ is very easy. NQ is simply just like our push. We can just add the element at the front. We are done. But if I say NQ is very easy. But if you want to say DQ means we are going to remove the element. We should not remove the element at the beginning. We have to remove the element at the end, which can only happen in two ways using linked list. Either
NQ
you need to
means,
navigate.
if I'm wrong, sorry. If I'm
Yeah,
wrong,
sorry.
NQ means adding the element at the end, right? If not, I'm wrong. In
Adding the element at the I think um, front and it's there is no, and like I would say front and rear. That's what, if I remember correctly. So Q has two things. Front, you will add at the one. Let's say this is front. You can think of this as a front, and this is a rear. So if you are enqueuing, you have to add at the front of the linked list, and rear, or maybe it's the other way around. So if you want to remove, you need to remove at the rear of the link queue, right? So NQ means, I agree with you. Basically, NQ means you need to add at the one end. Let's say your NQ means you are adding at the head, you are adding at the beginning, and you simply update the head value, the reference of the head, right? Very easy. NQ is just equal to our push operation we just discussed, right? But the only problem here is DQ, because DQ means you need to remove. You should not remove the first element, because if you remove the first element, it's just like a stack. You are inserting at the, and you are inserting at the head, and you are removing at the head. So if I say 5 and you insert NQ 5, you will insert 5. But if I say DQ, I don't want to remove 5. I want to remove the number one, right? So as you said, the only options are, either you need to navigate from header all the way to n minus 1. That means, let's say we have 1, 2, 3, 4, 5 and fourth element, and then update the next address. That way, this will go into the trash. The number one will go to the trash or taken care by the garbage collector. Or the other alternate thing is double linked list. So very, very important. Like, it's not important, it's kind of interesting. I don't want to say important. I don't think interviews will cover double linked list much, but it's very interesting. So double linked list is the best suited for implementing queue, because every node has two values. Double link, this is introduction to double linked list. Every node has basically two addresses, previous and the next, and here is the data. This is previous and this is next. So this previous will tell you what is the previous node, okay, and next will tell you what is the next node. So it's very easy to navigate. Now we can cover a lot of problems. At least I practiced 3 to 4 problems on double linked list. I can explain. So this double linked list will, at any point of time you can navigate either directions. So that's a beautiful kind of data structure. This is really helpful to implement the queue. So I think this is a follow-up question for every interview question of this stack. If I say implement a stack using linked list, you will complete in 20 minutes. The next question is, hey, how do you implement a queue using a linked list? Then you have to explain the same thing. Hey, these are the problems with single linked list. If you want me to implement with double linked list, this is the way I can do it, because this last node, I can r rare will give you the last node, and using this previous pointer I can access number 2, and then I can make this null. Very simple, right? The rare, this here is the head and here is the rare. This rare will go to the last point, and I can go back to the previous, what is the previous value here, and then I can go to the previous element and I can update the next address of the previous to null. That makes the DQ operation very easy, right? Is it am I going fast, or is it clear? I want to know the response here. Cislia or Karanya. I think Vinila followed, I think, because she told that double linked list.
Yeah, it is clear.
Yeah,
Yes.
cool. Yeah, so this is a very interesting topic we discussed today. I think next week I will try to come up with this algorithm. It's you can write it like it's kind of, if anyone have some time this week, definitely I will encourage you to write this implement queue using double linked list. So otherwise I will try to write it and I will show you next week. So I think it's almost like 10 and it's 10:30 in India. Maybe we can discuss the next algorithm next week. This one, creating a copy of immutable list. This is also kind of cloning, interesting problem. So otherwise, we can. I will stop here. So let me know any other questions so far. Okay, is it helpful? Any questions? Shivgar, any questions from your side?
No,
The-
sir.
what's
Very, very helpful, sir. Very, very interesting. It's just like refreshing our memory and making us to think again, I think.
exactly, that's the main intention here. Even it's helpful for me as well to think and understand, like, kind of. Yeah, it's yeah, thank you for that. You can just call me Suresh, like, I don't want to like Garu or anything. I will also call you just Shiva. That will be easy,
Sure.
communication, yeah.
Sure,
So
sir. Sure. Thank
cool. Yeah, if no other questions, we can wind off and we can continue next week. Okay,
Sure.
have a
Thank
nice rest of the week and have a nice week ahead, and we can meet again. Yeah,
Thank you.
thank you
Thank you so
everyone.
Thank
much.
you.
Thank you.
Bye,
Thank
Suresh.
you. Bye bye.
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 Great.